This video is going to be discussing part 2 of transition metals and their chemistry, and so we'll be focusing on colors and specifically changing the oxidation numbers. So let's start. So colors of transition metal ions can change due to the changes in the oxidation numbers, ligands, and coordination numbers. But in this video, I'll be looking more on the oxidation numbers changing using vanadium. Okay, so these are the colors of vanadium at different oxidation states. So we have VO2 plus, which is yellow, and vanadium's oxidation state would be 5 in this case. And VO2 plus, it's pronounced the same as VO2 plus in the yellow, but this guy is going to be blue, where vanadium has an oxidation state of +4. And V3 plus is going to be green, V2 plus is going to be purple. So as you have noticed, the vanadium is being reduced, right? So we're going to see the interconversion of vanadium's oxidation states using the electrode potentials using zinc. Okay, so we're going to first of all discuss the reduction from +5 to +4. So we have VO2 plus 2H plus E electron, and VO2 plus H2O. So this is a half equation of reducing the vanadium in this case, and the electrode potential for this half equation is going to be +1.00 volts. And we have the zinc being reduced. This is the reduction potential, so it's in the reduction direction, but we're going to flip it in a minute. So the electrode potential for this one is going to be -0.76 volts. Okay, so I have those half equations over there. So first we want to reduce the VO2 plus, so zinc has to be oxidized, right? Therefore we need to flip zinc's equation. So over here now zinc is being oxidized, right? It's losing the electron. So then we must balance the number of electrons. So as you can see, the first half equation, it has only one electron, yeah? So we need to multiply this by 2 so that we can balance out this 2 electrons on the zinc's equation. So I have done that. So we have 2, 4, 2, 2, 2 as our stoichiometric ratio now. Now we need to add the equations so we can cancel out the electrons, okay? So we're going to use simultaneous equations and end up with this. So as you can see, there are 2 electrons on this side and 2 electrons on this side as well. So we can cancel them out and get the overall ionic equation, the full ionic equation as seen below. So with this equation that we deduced, let's calculate the cell potential of this reaction to see if the reduction is feasible. Keep in mind that cell potentials would be feasible if it is positive, okay? I mean, the reaction will be positive when the cell potential is positive. Feasible, yeah. So cell potential is equal to the potential where it's being reduced and the potential of oxidation minus the potential of oxidation. Okay, so that is a formula for working that out. And we knew that the reduction potential of vanadium oxide was the ion is +1.00, and for zinc's reduction potential we had -0.76, and we know that zinc was being oxidized, right? So that has to go in here because it's minus oxidized, and then the vanadium's it has to be on the reduction potential. So overall, the cell potential is going to be +1.76, okay? Please try and do this by yourself and check your answers as well. And this is positive, right? So therefore, this reaction is going to be feasible. And you'll know because you will see the color changing from yellow to blue, because this with the oxidation state of +5 was yellow, and when it became 4, it turns blue, okay? Now we're going to look at the reduction from +4 to +3, still using zinc, okay? So we have this other half equation where we have VO2 plus being reduced into V3 plus and the zinc's reduction half equation as well. and we have the electrode potentials for those as well. So again, we're going to flip the zinc's reduction equation, and we're going to balance it and balance the electrons, and we're going to cancel the electrons using simultaneous equations to get this overall equation. So try it by yourself and check the answer. Okay, you can pause the video and try it. So with this deduced, now we know that the VO2 plus is being reduced and the zinc is being oxidized, right? So again, we're going to plug that, we're going to use this to use the formula to calculate the cell potential. So this had the value of plus 0.34, minus 0.76, and we have the cell potential, which is equal to the reduced potential and the oxidized minus the oxidized potential. So we're going to end up with a value of plus 1.10 volts, which is still positive, right? So the this reaction is going to be feasible, and you'll see the color changing from blue to green, as we know that V3 plus is green, okay? So now, lastly, we're going to look at the reduction from plus 3 to plus 2. So we have the vanadium ion, 3 plus ion, being reduced to V2 plus, and we have zinc's half equation again. And the electrode potential for this half equation is minus 0.26 volts, okay? By the way, electrode potential and reduction potential is the same thing. I'm going to basically multiply this equation by 2 because we need to balance the number of electrons, and I'm going to flip the zinc's equation because it's a reducing agent, so it has to be oxidized, and we get these, and now I'm going to use these simultaneous equations to work out the overall equation. Okay, so we have 2 V3 plus ions plus zinc, reversible sign, and we have 2 V2 plus and zinc 2 plus. Okay, so let's work out the cell potential. So V3 plus is reduced, so this potential has to go to the first bracket, and minus 0.76 going to the second bracket, and do the minus, and then you will get plus 0.50 volts, okay? So that is our cell potential, which is still positive, and therefore this reaction over here, this overall reaction, is feasible. So you will see the color changing from green to purple because we know that V2 plus is a purple ion, okay? So let's see if we can reduce the vanadium 2 plus into just V, the element V, which has an oxidation state of 0. Okay, so we have the half equation again with its electrode potential, which is minus 1.18 volts. Okay, so if we want to reduce that, we need to first of all flip this again, right, and get the overall equation, repetition from what we have been doing. So if you just plug that into the formula again, you will get a negative value. So it's minus 0.42 volts now. So this is a negative cell potential, which means that this overall equation, this is not going to be a feasible reaction, okay? So the reverse reaction, the backwards reaction, V becoming V2 plus is going to occur, but the forward reaction is not going to occur, okay? So yeah, we cannot reduce V2 plus into V using zinc, okay? It can only be reduced from V3 plus to V2 plus, and that's it, okay? So that was it for vanadium, and in the next video, in part 3, I will be discussing more about chromate ions and just chromium in general, okay? So see you in the next video.